Okay, welcome ladies and gentlemen to this video lecture. Let's take a look at this example. So we want to prove using the definition that the limit as x goes to minus 2 of 2x squared plus x minus 2 is equal to 4. So as before, let's write out exactly what we need to prove. You can do this as an exercise. We need to prove for every epsilon greater than 2 there exists a delta greater than for every epsilon greater than 0 there exists a delta greater than 0, so that if absolute value of x minus 2 is greater than 0, less than delta, then this expression is less than epsilon. That is what we need to prove. And as an exercise, what you should do now is also write out your proof outline before you start. So I would suggest pause this video, write out your proof outline before you start. So pause this video now and write down your own proof outline and compare to what we have. So old hat. Proof outline we want to show for every epsilon. So we fix any epsilon. We need to show that there exists a delta, so we must define it. So we say define delta, leave a space, and right here, what are we allowed to use? We are allowed to use epsilon in defining our delta. That is the only symbol that we are allowed to use. Then we want to show that if this happens, then that happens. So we assume the hypothesis, and finally we must conclude that this expression that we have down here is less than epsilon. Okay, so here we have our proof outline. Let us fill out our proof now. And you will see something strange happen. Let's look at our previous example. So in our previous examples, what we had is we ended up with the expression that we want to get less than epsilon. We got that less than some constant times delta. And since we had it less than some constant times delta, we could, by choosing our epsilon as 1 over that constant, or choosing our delta as 1 over that constant times epsilon, we could force this expression that we want less than epsilon to be less than epsilon by choosing our delta in this way. Now in this coming example, this will not happen. So keep your eye out for how we will not have a constant here. We will get an expression in terms of x. So let's see how that happens. So what I'm going to do is I'm going to duplicate this page, and I'm going to fill out our outline here. Okay. So what I'm going to do, let me erase that and replace that, because minus 2 is plus 2. What are we interested in? We are interested in this expression, 2x squared plus x minus 2 minus 4. If we simplify, 2x squared plus x minus 6. This is, if we factorize, that is 2x minus 3 x plus 2. And since we've assumed, you see here again we end up with the same expression, and we've assumed that that expression is less than delta. So we end up with 2x minus 3 is strictly less than delta. Okay, and now notice here, previously we had a constant multiplied with delta. Here we do not have a constant. Okay, this is a problem, because previously you see here we had this constant 2 times delta, and that allowed us to just define our delta as 1 over 2 times epsilon. Here we do not have that luxury. So we must take care of this expression here. How will we do that? Or what do we have control over? The only thing that we have control over, that we are allowed to choose, is this delta. That is the only thing that we have control over. Let us think about this expression. And how can we force this expression to be less than a constant? Okay. Let's think about this function. Let's think about the function that sends x to the expression 2x, what is it, minus 3. So the graph of this function, this is just a straight line. It looks like that. It has an intercept there at minus 3 and it has a slope of 2. We are interested in the limit at minus 2. So over here, minus 2. So what are we doing? We are, by choosing our delta, we automatically restrict ourselves to an interval around minus 2. And we see here, if we, let's just say we take the interval of radius 1 around 2. So let's think about what happens on the interval, closed interval from minus 3 to minus 1. So on this interval. From the graph, you can immediately see that the absolute value of the function takes on a maximum here at minus 3. And what is that? If you plug in minus 3, that looks like 2 times minus 3 is minus 6, minus 3 is minus 9. Absolute value of minus 9 is 9. So for x in the interval minus 1 to minus 3, actually the other way around, minus 3 is smaller than minus 1, minus 3 to minus 1, we have that 2x minus 3 is less than or equal to 9. This is a claim that we are making. Let us prove this claim. Proof of claim. And let's write it this way, or let's write it this way. So if x plus 2 is is less than or equal to 1, then 2x minus 3 is less than or equal to 9. And you could even call this a little lemma if you want. What is a lemma? A lemma is just a short little result that you use in proving some larger result. Let's prove this. Proof. You see we have an implication here. So we will assume x plus 2 is less than or equal to 1. Then we've got, by definition of the absolute value, x plus 2, this is less than or equal to 1 or greater than or equal to minus 1. That is just from the definition of the absolute value. Now let's rework it into that form. So Let's multiply everything by 2 to get a 2x. So that's minus 2 less than or equal to 2x plus 4 less than or equal to 2. We are looking for a minus 3 here, so let's subtract 7 everywhere. So minus 2 minus 7 less than or equal to 2x plus 4 minus 7 less than or equal to 2 minus 7. That becomes 2x minus 3 is less than or equal to minus 9 and less than or equal to minus 5. Therefore, the absolute value of 2x minus 3 is less than or equal to 9. This is again by using the definition of the absolute value. Okay, so we see here, if this expression is less than or equal to 1, then this expression is less than or equal to 9, and most importantly, it is less than or equal to a constant, and the constant is 9. So we see here, if we can force this expression x plus 2 in absolute value to be less than 1, less than or equal to 1, we can force this expression to be less than or equal to a constant. If we go back to our proof, if we can force this expression to be less than or equal to 1, we can force this expression to be less than or equal to 9. How will we do that? What control do we have? The only control that we have is in choosing our delta. So let's put a 1 here. Okay. So since delta is, and I'm going to write here less than or equal to 1, we have that x plus 2 less than delta is less than or equal to 1. So let's give this lemma a name. Let's call it A. So by A, we've got 2x minus 3 is less than or equal to 9. So here is our reason for our following inequality. Here we get 9 equal to delta. Okay, so this part justifies this inequality. Good. And now finally we want to get our 9, or this expression 9 delta, to be less than or equal to epsilon. Okay, so again, now how will we do that? What is the only control that we have? The only control that we have is in choosing our delta. So why don't we also need to somehow bake in an epsilon over 9 here. Okay, but we need delta to be less than or equal to 1 to get this constant here, and we need our delta to be less than or equal to epsilon over 9. We need both of these conditions to hold. So how will we force our delta to satisfy both of those conditions? We take the minimum, the smallest one of these two. If we take the minimum of 1 and epsilon, we define delta to be the minimum of 1 and epsilon over 9. Then we have delta is less than or equal to 1 and delta is less than or equal to epsilon over 9 at the same time. So since we have this, we automatically get this for free, which gives us our constant 9 here. And since we have this, we can fix this delta here to get an epsilon. So this will give us here that this is less than or equal to 9 times epsilon over 9. 9's cancel. That is equal to epsilon. Okay. And now we're done. Now we are done. So let's read this. So we fix any epsilon. We define our delta as the minimum of 1 and epsilon over 9. Why do we define it to be this way? Because, why do we have the 1 there? Because here we want to have, we have this non-constant expression here, which we want to bound by a constant. So all we do is we restrict our view to a closed interval around -2, and we ask ourselves, what is the maximum, or can we find some bound for the absolute value of this expression? And if we think a little bit, if we restrict ourselves to this interval, the interval of radius 1 around -2, we obtain that this expression is less than or equal to 9. So that is why we have the 1 here. And since we have the 1 here, the minimum of 1, delta is less than or equal to 1. So here we've got, since delta is less than or equal to 1, we've got 2 plus x is less than or equal to 1. But here we have shown that if that is the case, then this expression that we're interested in is less than or equal to 9. So this gives us this part. So this allows us to get this constant over here. And once we have this constant over there, we can see that since we want this thing to be less than epsilon finally, we need somehow to bake in an epsilon over 9 here. So delta less than or equal to an epsilon over 9. So over here, that is why we put in the epsilon over 9 there. And we choose the minimum of the two, because we want delta to be less than or equal to 1 and epsilon over 9 at the same time. And if we choose delta to be the minimum of 1 and epsilon over 9, that is automatically true. That is by definition of the minimum. And when we choose our delta that way, we end up with this expression that we're interested in, less than epsilon. Okay. So that is it for this example. We will do another one, but that will have to wait until the next video. I will see you in the next one.